Hi there. During this session I'm going to be putting together the various processes of thermodynamic change which we've spoken about into a cycle. So these processes are going to create a cycle which can be repeated again and again and again, very much like what we see with the combustion engine. So let me take you through, kind of build up a cycle, and then I'm going to look more specifically at the kind of thing we get actually in a combustion engine. So here's a simple cycle. If I consider a gas and the change, we have an isobaric change where the pressure stays constant and the volume increases. Then I can have an isochoric change, and in this case the volume stays the same as the pressure changes. And then next I can have a compression, so some work would need to be done here. And then I've got a volume change, and then I've got a further compression with a gas change. Now we've got to remember here that the work done is equal to the area underneath the curve. Okay. But the thing to recognize is that if we're increasing the volume, that means that what we have here is work done by the gas, with the pressure being the same. Now, here's an example question, okay? So the graph shows a variation of volume with pressure of a system, okay? So it's a rotating system. What work is done in compressing the gas from R to P? Okay, so thinking about what work is done here, we just look at the options and we know that the work done is the area underneath the graph from R to P. So that means the work done on the gas is 3 times 10 to the 5 joules. That's how much work has been put in to cause this compression. Now, the thing to recognize here is if we're compressing, the work done on the gas will be the area underneath the curve, and what we have is the cylinder expands, we've got the work done by the gas, and that means that net work done by the gas is equal to the area enclosed. So that means the net work done is the work done on the gas, or actually the work done by the gas in total minus the work done on the gas gives us the net work done. And that net work done tells us exactly how much energy has been transferred by this process. Okay, so this is my kind of simple example. Now, the real world is a little bit more complicated than that, so let me take you through a real world situation. Now what we have here is that it's very, very difficult to maintain a constant pressure change. So what we have is in a piston, so this is a piston, and imagine what's happening here is that we're going through a cycle, and I'm going to talk about this cycle in more detail, but as we can see we have isothermal changes and adiabatic changes, and then isothermal compressions and adiabatic compressions. And that allows us to go through a loop, and this is actually what happens in a piston engine. Okay? So it's not the simple rectangle, but still the net work done is still going to be the area of the shape in the middle of this cycle. So let me talk about these bits in detail, the stages in detail. First of all, we have an isothermal compression. So that means the temperature stays the same whilst we're compressing the gas. And then we have what's known as adiabatic expansion. So there's that expansion. And then we have an isothermal compression. And then we have a further adiabatic compression. Now this process, as we can see, is cyclical. Okay, we end up with the same pressure each time, and what we can do here is by having this process, it allows us to produce an engine which we can get to do work for us. Now that is obviously exactly what we have with a combustion engine. So think about some questions related to this here. This diagram shows the pressure volume diagram for one cycle, PQRS, okay, of an engine. In which section of the cycle is work done on the engine? Okay, so we're thinking about which section of the cycle is work done on the engine. Now, hopefully you've worked out the work is done in this situation in the P to Q only, okay, because that's the only section where we're having to compress the volume and there's an area underneath the graph. Okay, so what we have here is this section here underneath that line, that's the one where work is being done on the engine, and everywhere else in the cycle the engine or the gases involved in the engine are doing the work. So think about another set of questions here. Okay. I've got a quantity of an ideal gas is used as working substance of a heat engine. The cycle of operation of the engine is shown in this PV diagram. Okay, so we've got going around A to B, B to C, C back to A again. Okay. The gas at A is 300 Kelvin. Calculate the temperature at B of the gas. It's the first question for you to do. During the change A to B, the change in internal energy of the gas is 7.2 kilojoules. Determine the amount of thermal energy transferred. And the third question is state why change B to C, the change in the internal energy of the gas is numerically the same as that is in part B. Okay, so let's take you through some answers here. First of all, if we recognize that the pressure is constant, that means the ratios of the initial volume and the initial temperature divided by the final volume and the final temperature are going to allow us to work an unknown, and that means that the temperature is going to be 900 Kelvin. The next feature is the work done is equal to the pressure times the change in volume. So that gives me a value of 4.8 kilojoules. We've also recognized that the amount of energy overall transferred is going to be equal to the work plus the change in temperature. So what we can do here is we've got my work done plus my change in internal energy, so that means the total transfer of energy, transfer of heat, is going to be 12 kilojoules. Final question is state why the charge change B to C, the change of internal energy of gas, is numerically the same as the change in B. Okay. Now in this case what we can recognize is that the magnitude of temperature change is going to be the same, and as the gas is ideal, so therefore the change in internal energy should only depend on the change in temperature, so it should be consistent all the time. Hopefully that's given you some insight into these thermodynamic cycles and how they can be used.